So welcome everybody. My name is Greg Bleckerman, and it's a great pleasure for me to introduce Mauricio Velasco. Mauricio received his PhD from Cornell, and then he was a Maury assistant professor at UC Berkeley. But since his undergraduate days, Mauricio retained an interest in economics, and so then he went to work for Goldman Sachs. But fortunately for us, that work left him unfulfilled. And he came back to academia after 1 year. And now he is an associate professor at Universidad de los Andes in Colombia. And his work has been recognized by Jose Fernando Escobar Prize in 2017. This is a triennial prize, so given once every 3 years for, let me quote, most significant national achievement in pure and applied mathematics by a Colombian mathematician is given by the Colombian Math Society. So Mauricio has a very broad set of mathematical interests. He is always extremely enthusiastic about mathematics, and I'm looking forward to an excellent talk.
Can you hear me? Yes. Okay, thank you, Greg, for your very kind introduction. So I want to begin by thanking the organizers for this wonderful conference. I'm really happy to be here. This is my first time in Switzerland, and the conference itself has been wonderful. And in particular, I feel very honored by the privilege of addressing this audience and of telling you about some of the things we have been thinking about in the last few years. So the title of my talk is Two Regular Varieties and Their Applications. And I am going to begin sort of from the end of the talk. I want to begin with the take-home message of the talk to make sure that no matter what happens in the next 50 minutes, there is something that you bring with you. Because I think that there are two important ideas, which is what I will try to convey, but I don't know if I'll succeed. So let's state them bluntly. So the first idea is that there is a class of projective varieties which are, objectively speaking, the simplest that are not linear subspaces. So the simplest varieties are certainly linear subspaces. These ones are the next simplest. And they are called two regular varieties. Maybe they have a naming problem, and this is why they are not as popular as they should be. But this is the name. There are two regular varieties. And second, perhaps because of their simplicity, they appear prominently in many parts of mathematics. They appear in combinatorics, in classical algebraic geometry, in real algebraic geometry, in convex geometry, and in many other areas, graphical models, numerical linear algebra, many, many others. And because of that reason, I think it's important to know about them. And this is why I thought that this was a good topic for a general audience. So the aim of the talk is that after it, you will know what two regular varieties are, and you can use them in your research. You can use them to try conjectures, to test cases, and sometimes to answer difficult questions. This is precisely what the tool you need. So now, specifically, the talk is going to be split into 3 parts. The first one is I will try to explain what do we mean by simplest varieties. So I will describe an objective measure of complexity, not in the sense of computational complexity, but just in the sense of difficulty of a variety. And then we will define two regular varieties as those for which this difficulty is as small as possible. Then we will look at where these varieties arise, let's say in nature. So they turn out to appear prominently in graph theory and in classical algebraic geometry, so I will describe those in detail. And finally, in the last part of the talk, I will explain some joint results with Greg Bleckerman, Rainer Sinn, and also Greg Smith, in which we have done several things on two regular varieties, and we have discovered that they play a prominent role in this sort of new area of mathematics called convex algebraic geometry, which is the interaction between real algebraic geometry and convex geometry. So I will explain a little bit about what this is about, and then talk about two regular varieties there. So let's begin. What are the simplest varieties? So suppose that S is the polynomial ring in variables x0 up to xn, and that we are given an ideal I, which is radical and which is defined by homogeneous polynomials. And someone asks us the question, how do we understand the geometry of the variety defined by those homogeneous polynomials? So this is a very vague question. What do we mean understanding? So maybe one possible interpretation is this sort of black box understanding, that we have some list of varieties that we understand, whatever that means, but it's some list that we have. And our aim is to decide whether the solution set of our system of equations belongs to that list or not. Now, how do we construct the list? Well, this is the point of algebraic geometry. We have been classifying varieties for hundreds of years. And now let's think only about the problem of where do we put this system of equations. So in order to do that, what you normally would do is try to compute numerical invariance of the solution set. So you would begin by determining the dimension. Then maybe, since you are in projective space, you look at the degree, but there are many varieties with the same dimension and the same degree, and so you have a need for deeper, finer invariance. And it turns out that commutative algebra provides for us a lot of these invariants, one of which is the so-called Betti table of X. So from the generators of I, we can construct a matrix of integers called the Betti table of X. And the way in which you should think of this Betti table is, imagine it's a large matrix, and its different columns have an interpretation. So the column labeled 1 records the degrees of the minimal generators of our ideal I. The column labeled 2 records the degrees of the relations between those generators. By relations, what I mean is, imagine linear combinations of your polynomials, but with polynomial coefficients. So I'm looking at the set of these relations, and I look at the generators of this set of relations, and that has some degrees. And then I look at the degrees of the relations between those relations, and I continue. And the theorem of Hilbert guarantees that this process eventually stops. So my matrix is really finite. With a little bit more precision, what I'm trying to say is, let R be the quotient of the polynomial ring by the ideal. The graded S module R has a unique graded minimal free resolution, which is an exact complex like the one that's drawn on the slide, where the modules F sub I are called the CCG modules, and are simply direct sums of the ring with certain various degrees. And now once you have this complex, which is unique up to isomorphism, you can write down the Betti table of X as a matrix, where what you need to remember is that the ijth entry of this matrix remembers how many generators in degree I plus j are there in the jth CCG module. Now suppose that this description I just gave made absolutely no sense to you, that you never did any commutative algebra or you don't care. Even in that case, you can still use Betti tables. The reason is that there is this fantastic computer program called Macaulay 2, in which you simply write down your equations and then you write Betti, and the computer tells you what the Betti table is. So even if you don't understand where these numbers come from, you can still use them productively. And I think that that's important. So let me give you a concrete example. If you take I to be the ideal generated by xy, xz, and yz, then the minimal free resolution turns out to be the complex that's shown in the upper part of the slide, and the Betti table is this matrix that's written here. Now, how do you read the matrix? The important thing is that the columns 0, 1, and 2 correspond to the module, to the 0th CCG module, to the first CCG module, and to the second CCG module. For instance, the way you read the entries is you have a 2 here because your second CCG module, namely this guy, has 2 generators in degree 1 plus 2, which is 3. Why are they in degree 3? Because the columns of this matrix are linear on quadrics, and therefore they should have degree 3. So that's all. You simply look at the minimal free resolution and write down this table. Now, when you look at Betti tables, the first thing, okay, and these dots simply mean 0. Okay, I'm only drawing the things that are non-zero. So when you look at Betti tables, especially of varieties with a little bit of structure, you will see that these numbers are very much not random, that they exhibit certain, for instance, surprising symmetries. If you take the ideal of the Grassmannian of lines in P5, what you see as Betti table is this picture here, and observe that you certainly have symmetry. This is very much not a random choice of numbers. And it is a very natural question to ask, what do Betty numbers say about the geometry of a variety? And this has been one of the driving forces of commutative algebra over the last 20, 30 years. Is this geometry of CCG's program. And this is an area that has many, many results. For instance, you can know from this Betty table that the Grassmann lines is arithmetically Gorenstein, which is a rather delicate property of the ring. And among these results, there is an understanding that the size of this table is a good measure of how complicated a variety is. And this measure of the size is the Castelnuovo-Mumford regularity. So the Castelnuovo-Mumford regularity of a variety X is the number of non-zero rows of this Betty table. So our first example is a variety of Castelnuovo-Mumford regularity 2, and our second example is a variety of Castelnuovo-Mumford regularity 4, because there are 4 non-zero rows. Now, what is the regularity? Well, the regularity essentially bounds the degrees of all generators of all CCG modules. Specifically, the degrees of the generators of the J CCG module are at most the regularity plus J minus 1. So this is really a number that measures how big is the degree of your generators. And in that sense, a measure of complexity. But this is not the only sense. So regularity has another interpretation, which was Mumford's original definition, reinterpreting Castelnuovo's work cohomologically, as a quantitative measure of cohomological vanishing. For those that know a little bit more, is a kind of quantitative version of the Serre vanishing theorem. This is what regularity does. There is no time during this talk to really explain what this means, but let me focus on a specific example on what this interpretation says in the case of points. So suppose that X inside of Pn is a finite set, okay? We know that the set of functions from any finite set to a field, to, let's say, over the complex numbers, is a finite dimensional vector space. And because of that reason, basically, every function can be written as a polynomial. Okay? For every function that you choose, whatever in a finite set, there exists a polynomial that realizes it. But the key question here is, how much of a degree does that polynomial have to have? So if you have more points, or if these points are located in a complicated position, you will need higher and higher degree in order to be able to express all these functions. And that's what the concept of interpolation degree measures. The interpolation degree of a set of points is the smallest d, such that every complex valued function on the set of points is a restriction of a polynomial of degree d. And turns out that the interpolation degree is exactly the regularity minus 1. So I hope that this gives some plausibility to the idea that regularity measures complexity in some sense. So that's what regularity is for sets of points. Now, let's think about how do varieties of regularity 1 look like. Well, if a variety has regularity 1, this means that the Betty table has only 1 row, and this means that the generators of the ideal have to be linear polynomials, so your variety has to be a linear space. So a variety has regularity 1 if and only if it is a linear space. They are pretty important, but we understand them. So we add this definition. A variety X inside Pn is a 2-regular variety if it's non-degenerate and has Castelnuovo-Mumford regularity 2. So this term non-degenerate, which I will use a lot during the talk, is very easy. All it's saying is that your variety is not contained in any proper hyperplane in your space. Because if it was contained in a proper hyperplane, you would rather think of that as your ambient projective space. So that's something that you can always say without loss of generality, let's say. So what are these 2 regular varieties? Well, in other words, one can imagine this, or one can say these are varieties whose ideal is generated by quadrics. They must be defined by quadratic equations. But not only that, all matrices in the minimal free resolution of their ideal has to consist of linear polynomials. Or also, if you look at the Betty tables, those are the things in which the Betty table has only 2 non-zero diagrams. So now let's look at a specific example. Since we understand regularity for sets of points, let's ask, if you have a set of points that has regularity 2, what does that mean about the set of points? And well, this means that the interpolation degree of the set of points is 1, so that one can interpolate with linear functions. And if you think about that for a second, this is the same as saying that your points are linearly independent. So a finite set of points has regularity 2 if and only if it is a linearly independent set of points. So again, morally, you can think that two regular varieties are the variety version of the concept of linear independence. And maybe this is why they are so useful. So now what I will do is try to give you some examples of how two regular varieties appear sort of in nature. So if somehow you were lost and you're not interested in Betty tables or whatever, ignore that. We will basically start over. So just let's think of graphs for a little while. And specifically of a particular class of graphs. So a graph G is chordal if every cycle in G has at least one chord. A chord means an edge that crosses the cycle. So for instance, the graph on the left of this picture, the pentagon, is not a chordal graph because here's a cycle, the pentagon itself, that has no chord. There is no edge. There is no edge that goes across the cycle. On the other hand, the graph on the right is chordal because no matter which cycle do you pick, this cycle is always crossed by a chord. I suppose I should say every cycle of size at least 4 or something like that. Okay. Now, when you look at this definition, it doesn't seem to impose too much of a structure on graphs, but this is in fact the case. So chordal graphs are a highly structured class of graphs, and in order to see that, we will use a theorem due to Gabriel Dirac from 1961, the son of the physicist Dirac, which gives us another way of thinking about chordal graphs. So I will read the theorem. A graph G is chordal if and only if it is possible to totally order its vertices, V1, V2, up to Vn, in such a way that for every J, the set of neighbors of the vector Vj which appear before it form a complete subgraph of G. Okay? So this is not so easy a definition to parse, so what I will do is I'll show you an example. So I will draw a chordal graph by putting the vertices in the order which the theorem describes. So we begin with 1, then 2, then 3, then 4, then 5, then 6, and then 7. Now the important thing to observe is imagine or look at what I did when I put the fifth vertex. When I put the fifth vertex, what's important is that 5 is adjacent to 3 and 4, and that 3 and 4 formed a complete subgraph, in this case just an edge. In the same way, when I add 6, the important thing is that the neighbors of 6 form a complete subgraph. Okay? And notice that the ordering is important. I'm not saying that the neighbor of every vertex is that the neighborhood of every vertex is a complete subgraph, but only the part of the neighborhood which consists of vertices that come before in the ordering. Those have to be a complete subgraph. So this is one way of thinking of chordal graphs, and it's also a way of building many, many, many chordal graphs. If you understood this definition, now you can think of lots of different chordal graphs. And it is an easy exercise to show that this implies the definition in the previous slide, but in the other direction is a difficult term. Now, chordal graphs are extremely useful objects. They appear in numerical linear algebra, semi-definite programming, graphical models, and many other areas. And in my view, to first approximation, this is a consequence of two facts. First, a perfect elimination ordering, an ordering just like the one I described in the previous slide, allows us to work with chordal graphs inductively very effectively. So you can always think that chordal graphs are built by adding vertices one at a time with this perfect elimination property, and this allows you to prove statements about chordal graphs inductively very well. For instance, or as a consequence of this, several NP-hard problems admit efficient polynomial or even linear time solutions on chordal graphs. In a second, I will show you a concrete instance of this, but this is one of the reasons why we like chordal graphs very much. So that's the first one. And the second reason is that chordal graphs are very structured, but at the same time, a very rich class of graphs. If you take an arbitrary graph, then by adding a few edges, you can make it chordal. And through that, you can get information about arbitrary graphs from chordal graphs, typically just inequalities, but in many cases, this is the best that we have. So this makes them quite important. So let me illustrate this point one. How does one, let's suppose that somebody asks us, please find the size of the largest clique in a graph G. So it's well known that deciding whether this largest clique is at least a fraction of the size of G is an NP-complete problem. So we do not expect to be able to do this efficiently for all graphs. However, for chordal graphs, this turns out to be rather easy. So what I will do is I'm going to list the vertices in the perfect elimination ordering, and at each stage I'm going to look at the clique, at the complete subgraph, which consists of the neighbors of the vertex that I just added. So I start with 1, then I add 2, then I add 3, and that's my complete subgraph. Then I add 4, and this gives me a new complete subgraph. Then I add 5, then I add 6. And of course, when I pass from 5 to 6, turns out that my new clique is bigger than the previous one. Then I just forget the previous one, and I keep the larger one. And at the end, I have 1, 7. So by running linearly over the vertices of the graph, I have been able to not only find the largest, but actually enumerate all the maximal cliques on the graph. This is a problem that is extremely difficult for general graphs, but that for chordal graphs is easy. And so we know that in this case, the omega of G is 4, because this is the largest clique. Now let's move from graphs to varieties. So if G is a graph with n vertices, the non-edge ideal of our graph G is an ideal in the polynomial ring with as many variables as there are vertices, defined by the products xi times xj, where ij consists of the set of non-edges of the graph. Okay, so given a graph, you just look at which pairs are not edges, and you list those, and that's what we call the non-edge ideal ig. And of course, the non-edge ideal defines a variety because it's a radical ideal. And this variety is a union of coordinate subspaces because it's defined by monomials. Now, the geometry of these coordinate subspaces is fully described by the simplicial complex that we just looked at. So the irreducible components of xg are spanned by the subsets which form cliques. So we have 1, 2, 3, and 4 irreducible components. And the way in which these irreducible components intersect is encoded in the graph. So we really understand quite well how the varieties xg look like. So let's look in our example. What's the ideal ig? You just look at pairs of vertices that are not adjacent and write them down. This is your non-edge ideal. And that's the non-edge ideal. And if you, again, put this into Macaulay and ask what's the Betti table, the answer that you get is that the Betti table is this one, and in particular that it has only 2 non-zero rows. So for this particular example of a chordal graph, xg is a 2-regular variety. And in fact, this statement is true in general. And it's a good exercise if you want to understand chordal graphs, just use the perfect elimination order to prove by induction that every chordal graph is 2-regular. That's an easy exercise, and this is quite interesting. What is not so easy, but also true, is that the converse also holds. So this is a theorem due to Ralph Froberg that says that, I'll just read the theorem, let G different from the complete graph be any graph, and then it turns out that the following 2 statements are equivalent. G is a chordal graph, or xg is a 2-regular variety. So Froberg's theorem gives us a classification of those 2 regular varieties which are non-degenerate unions of coordinate subspaces. So now we know many instances of 2 regular varieties, those that come from chordal graphs. Is this clear? Yeah? Okay. So now let's move on to a different example. Let's think of, or let me tell you where 2 regular varieties appear in classical projective geometry. So in this part of the talk, I will ask my varieties to be irreducible. So let's suppose that x inside of Pn is an irreducible variety of dimension d. So recall that the variety x has degree e if the intersection of x with d generic hyperplanes is a finite set of cardinality e. Okay, so just to make this very clear, you have this 2-dimensional variety here, and if I want to compute the degree, what the definition that I had in the last slide tells me is that what I have to do is slice it with 2 hyperplanes and count how many points I see. So I slice it with one hyperplane, and I obtain this picture. Now the plane of the board is the hyperplane, and the blue thing is just the intersection. And then I slice again with another hyperplane, and what I get is 1, 2, and 3 points. And of course, I have to do this over the complex numbers, so no matter which choice I would take, I will always get 3. So this is why the previous picture is a hypersurface of degree 3. So dimension and degree are the two most fundamental numerical invariants of an irreducible projective variety. But it turns out that these two numbers are not independent. Degree and dimension cannot be arbitrary, and they are in fact related by this basic inequality. If x is irreducible and non-degenerate, then the degree of x has to be greater or equal than the codimension of x plus 1. And of course, when you see an inequality like this, it's natural to ask, what happens when the inequality becomes an equality? The inequality selects for you a special collection of varieties, which are the varieties of minimal degree, because their degree is as small as possible. A variety is called a minimal degree if it is non-degenerate, irreducible, and has the smallest possible degree it can, namely the codimension plus 1. And of course, it's again natural to ask, what are the varieties of minimal degree? And so I will give you two answers to this question. The first one is that we really understand what are the varieties of minimal degree. It's really good news. It's a result due to Del Pezzo and Bertini from 1880, which is really a complete classification of what varieties of minimal degree are, and is one of the great achievements of the Italian school of algebraic geometry of the 19th century. So it's really something worth learning. I'll just read it. So let x inside Pn be irreducible and non-degenerate. If x is of minimal degree, then either x is projective space, or x is a quadric hypersurface, or x is a cone over the Veronese surface, or x is a rational normal scroll. So if you don't know what these things are, maybe that's not so important. What I'm saying is it's an infinite list, but it's a list we really understand very well. Rational normal scrolls are many and very different. But if you maybe want a concrete example of a variety of minimal degree, the twisted cubic, everyone's first example of a variety which is not a hypersurface, is a variety of minimal degree. Has degree 3 in P3 and is a curve. So we do have a list and an understanding of what are all the varieties of minimal degree. But there is another way of thinking of what varieties of minimal degree are. And this is a theorem of Eisenbod and Xambo from 1984, almost 100 years later, which says that, well, I'll just read it. Let x inside of Pn be an irreducible and non-degenerate variety, then the following conditions are equivalent. First, x is a variety of minimal degree, and second, x is a two-regular variety. So, in words, the theorem of Eisenbod and Xambo classifies out of all two-regular varieties which ones are irreducible. And we know that very well. Those are precisely the varieties of minimal degree. I suppose every talk is supposed to have a proof, and so I'm going to try to give you a proof of this statement so that you understand at least how does one relate these kinds of conditions. Of course, it's going to be a fake proof. The key is in this italicized word typically, but let us ignore it for the moment. I'll just read this because I think that it morally explains why the theorem is true, although it's not an actual proof. So typically, the regularity of a variety x is equal to that of its generic hyperplane section. So you take a variety and you slice it with a generic hyperplane, typically the regularity doesn't change. This is false, but it's, I mean, for instance, for arithmetically Cohen-Macaulay varieties, it's true. I mean, there are some circumstances where it's true. Now, because of this fact, a reasonable way to try to understand this statement is to take your variety and your d-dimensional variety and slice it with d hyperplanes and see what happens. So I take my variety and I slice it with d hyperplanes, and what I obtain is a non-degenerate set, let's call it Z, of points in Pn minus d. Why do I get 2 points? Because every hyperplane drops the dimension by 1. Why do I get to Pn minus d? Because I started in Pn and I slice d times, so we end up with a set of points in Pn minus d. And my claim is that this set has regularity 2 if and only if x is of minimal degree. Why is that? Well, suppose that the set has regularity 2. Remember that a two-regular set is a linearly independent set of points. So what we are saying is that Z is non-degenerate in Pn minus D and is linearly independent. A non-degenerate linearly independent finite set must have n minus D plus 1 points, right? Because we are in Pn minus D, and therefore the degree of X, which is the cardinality of this set of points, is n minus D plus 1. So if a variety is too regular, if X is too regular, then it's of minimal degree. Conversely, suppose that X is of minimal degree. This would imply that Z has n minus D plus 1 points, and moreover, we know that it's non-degenerate, and from this it follows that it has to be linearly independent, which for points is the same as having regularity 2. So that gives us the other implication. The two are really equivalent. And of course, the only difficulty is that this typically is false, and this is where the work of Eisenberg and Xambon came in. They showed that these varieties are always arithmetically Cohen-Macaulay, so that this argument can actually be made. Yeah, so this is what varieties of minimal degree are. So far, what do we know about two regular varieties? Well, we know that this class contains the coordinate subspace arrangements of chordal graphs, and it contains the varieties of minimal degree, and this is natural to ask, can all two regular varieties be classified? And the answer is yes. There is a complete classification theorem due to Eisenberg, Green, Hewlett, and Popescu from the year 2004, which, if time permits, I will describe at the end. And if time doesn't permit, you're welcome to ask during the question session, how's the classification of varieties of two regular varieties, and I will explain. But now let's take a pause and let's try to, okay, so we have a kind of idea of what the regular varieties are. So let me tell you of something we discovered, which is that they appear in a surprising and very interesting way in real algebraic geometry. So to do that, let me just begin with some motivation from polynomial optimization, because otherwise what we do looks very, very artificial, and at least we believe is not. Yeah. So let's suppose that we are given a polynomial f in n variables with real coefficients, and somebody asks us, please find the infimum in all of our n of this polynomial. We want to find this number alpha. So what do we do? Well, something that one can do is note something. It's very, very elementary what is written here. So let P be the cone of non-negative polynomials in Rn, and note that for a number lambda, f of x is greater or equal than lambda for all x in Rn, if and only if f of x minus lambda is greater or equal than 0 for all x in Rn, if and only if f of x minus lambda belongs to P. Okay, so what I'm saying is a triviality, but conceptually is important. It allows us to change our point of view of optimization from taking a function and evaluating at points to rather thinking about the properties of a certain convex cone. And specifically, this means that we can, it follows that we can reformulate polynomial optimization problems as linear optimization problems over affine slices of this cone P. And in particular, our number alpha that we are looking for is equal to the largest lambda such that f minus lambda is greater or equal than 0. So this allows us to, instead of thinking of optimizing a polynomial by evaluating at points, we can think of optimizing a polynomial by studying a linear function over a slice of the cone P of non-negative polynomials. So because of that reason, the cone of non-negative polynomials, or even the cone of non-negative polynomials of a given bounded degree, is an object of enormous interest. If we were to understand it very well, where by understanding I mean obtaining a description which allows us to do linear optimization quickly, then we can really solve very many important problems that can be formulated in this way. But let's suppose even if we cannot understand all of P, if we only wanted to certify, to guarantee that a given polynomial f is greater or equal than a given value lambda, all we would need to do is prove that the polynomial f of x minus lambda is non-negative. So how does one prove that a given polynomial is non-negative? This is a very natural question. And I mean, there are many ways that one could try to do, but maybe the simplest one is you take your polynomial and you try to write it as a sum of squares of polynomials with real coefficients. Why is that? Because obviously a sum of squares of polynomials with real coefficients evaluated anywhere gives you a non-negative value because it's a sum of squares of real numbers. So we define sigma to be the cone of sums of squares of polynomials of some bounded degree. This is a typo I have on the slide, which I realized too late. So let sigma be the cone of sums of squares of polynomials of a given bounded degree. Then every sum of squares is non-negative, which is the same as saying that sigma is contained in P. And not only that, sums of squares are really very, very useful. And this is due to an observation of Lasser and Parrillo. It's not a difficult observation, but it's extremely important. It has produced an incredible amount of research, of which we saw a lot during this week. It's really a very, very important idea, which is that checking whether a polynomial is a sum of squares of polynomials of bounded degree is a semi-definite programming feasibility problem. And moreover, if you want to do the optimization we had in the previous slide, where you replace P by this sigma, then the optimization problem becomes something that you can solve, becomes a semi-definite programming problem. Maybe I should say this. So what is semi-definite programming? Well, it's a generalization of linear programming that shares with it many of its good features. Maybe the main one is that you can, at least numerically, solve optimization problems in polynomial time with it. So if I express something as a semi-definite programming problem, at least in theory, I should be able to solve it by waiting that computers get large enough. This is the idea. And not only in theory, in practice, semi-definite programs work, at least of modest size, work extremely well. As the size grows, there are scalability issues, but okay, that's a different matter. So the point is, and what I'm trying to get at, is we have two cones, and they are important for completely different reasons. One is the cone P of non-negative polynomials, and the other is the cone sigma of sums of squares. We like P because it encodes the important problems. P is the one that allows us to do optimization, and we like sigma because on it we can do computations. And so, of course, it's a very obvious question. When are we in the best of possible worlds when these two things agree? Is every non-negative polynomial equal to a sum of squares? And the answer is that sometimes it is, sometimes it's not, as David Hilbert proved in the year 1888. So let me more precisely frame the question. So is every non-negative homogeneous polynomial in n plus 1 variables with real coefficients of degree 2d equal to a sum of squares, and equal to a sum of squares? That's the question he tried to answer. And indeed he answered it. Equality holds if and only if we are in these situations. If and only if you're thinking of quadratic forms in any number of variables, or bivariate forms of any degree, or in this exceptional case of ternary quartics. And I mean, this is, let's say, good news and bad news. It's good news because in cases where they agree, it means that the alpha SOS that I had here is in fact equal to alpha, so that I can do optimization rather well. And in the cases where it's not, means that we need different ideas. And those different ideas have been developed. I simply will not talk about them now, but this is something that one can do in practice rather well. But what I'm more interested in is to ask, well, are there other situations in which non-negative polynomials and sums of squares coincide? Can we find other kinds of polynomials? For instance, let's think of, I don't know, multi-homogeneous forms or other things. This is why these, in quote, situations in which non-negative polynomials and sums of squares coincide. And okay, this is a rather vague question. So what I will try to do is give a context in which we can answer it completely. And this context is that of real projective varieties. So let me give you a quick background slide on what is this real algebraic geometry. So by a real projective variety X inside of Pn, we mean the set of solutions, both real and complex, of a system of homogeneous polynomial equations with real coefficients. The difference is that now my equations have real coefficients. And then, of course, such a variety has a graded coordinate ring, which is now real. So basically, I just take the ring of polynomials with real coefficients modulo the ideal defined by my equations. And it also has a collection of real points, which I denote in this way, x of r, which means just the points in projective space which have at least one affine representative, all of whose components are real. And any one of these varieties has two very natural cones, analogous to what we described earlier. So the first one is the cone of non-negative quadratic forms on X, which is precisely the convex cone in R2, given by those quadratic forms which take only non-negative values at the real points of X. So those are non-negative or real points of X. And the other one is sigma X, which is the set of sums of squares of linear forms in R2, which is precisely those quadratic forms that can be written as sums of squares of linear forms. And I'm going to try to understand the relationship between the cone P and sigma. And of course, when you're dealing with convex geometry, typically convex cones come with a dual pair. So this area, which I mentioned at the beginning, called convex algebraic geometry, tries to understand what is P, what is sigma, how do they relate, and the same questions about their duals. Yeah. Of course, maybe just one comment. When you see this definition for the first time, you might think, but why restricting only at quadratic forms? In principle, you could define both P and sigma to be forms of any even degree. So why quadratic forms? The reason is that I want to look at arbitrary varieties. So forms of degree 2D in an arbitrary variety Y is the same as quadratic forms on the dth Veronese embedding of that variety. So as long as I'm willing to consider all varieties, I might as well restrict to quadratic forms. And so this is why the question is framed in this setting. So yeah, as before, the inclusion sigma X inside Px holds. As before, Px is important for optimization. And sigma X is a cone on which we can do optimization. And thus, it is natural to ask the following fundamental question. For which varieties X does the equality sigma X equal to Px hold? And the answer, which is joint work with Gregory Bleckerman and Rainer Sinn, is that, well, let me just read the theorem. The answer to the question is that these are precisely the two regular varieties. It's an if and only if. So let X be a totally real, non-degenerate, proper subvariety of Pn, then X is a two regular variety, if and only if the equality sigma X equal to Px holds. So in a sense, two regular varieties are these best of all worlds, these ideal worlds in which you can do quadratic optimization via semi-definite programming in an exact manner. Now, what to do about this theorem? So in the time that we have, let me just briefly mention some consequences. So yeah, before I get into the details, the point is that this theorem allows us to organize all results about sums of squares and non-negative polynomials that existed in the literature about equality between these two things. And makes us see that they are really just manifestations of a common single idea, which I will later discuss. So so consequences, if I restrict to irreducible two regular varieties and remember that those are varieties of minimal degree, then we can obtain results, earlier results which we had proven with Greg Bleckerman and Greg Smith, relating sums of squares and varieties of minimal degree. And from that theorem, we can obtain results of Choi, Lam, and Resnick on multi-homogeneous sums of squares, of Jakubowicz on sums of squares on quadratic and quadric hypersurfaces. This Jakubowicz is a very common and used lemma in control theory. And of course, we can also recover Hilbert's 1888 theorem, and in particular, we can give a geometric explanation to this weird exceptional case that you saw in the previous slide. It turns out to correspond to the weird exceptional case, which is the Veronese surface in P5. And now, of course, this is what you can say if you look at irreducible to regular varieties, but there are many more to regular varieties. So if we restrict to coordinate subspace to regular varieties, and remember that these come from chordal graphs, we recover results of Groen and Johnson about chordality and positive semi-definite matrix completions that are also quite useful. Yes?
The Jakubowicz result is rational normal.
That's perfect. Okay, thank you. So what is the quadrics on quadrics? Oh, the S lemma, that's right. Yeah, okay, this is important, especially because in the audience there might be people who actually use the S lemma. So a consequence of this theorem is the S lemma. Thank you, Rainer, you're right. Okay, so what are the ideas of the proof? This is a slightly technical slide, but I think it's worth it. If you have bared with me all this long time. Let me just give you something so you can. Okay, so the ideas of the proof are mainly two. The first one, which is an idea of Greg Bleckerman. So Bleckerman discovered that the cone sigma x dual to sigma x is a special kind of convex set called a spectrahedron. And he really used the facial structure of this special cone. As a result, every extreme ray of the dual cone has a rank. Every point in the dual cone is a symmetric matrix and therefore has a rank. And it turns out that the equality holds if and only if every extreme ray of sigma x dual has rank 1. So this is basically a big conceptual shift. In order to understand these kind of statements, what we need to do is look at the dual of the sum of squares cone and try to understand the extreme rays of this cone. And if you want a difficult open problem, please describe the extreme rays of sigma x dual for every variety x. And then the second idea is that turns out that the ranks of these extreme rays are related with the entries of the Betti table of X. This is maybe the key technical tool or maybe a key result of our paper, which is that if the resolution of R is linear for P steps, then the minimum rank of an extreme ray of sigma x dual, which is not 1, is at least P plus 1. Okay, so what this is saying is that if you look at the third row in the minimal free resolution, the longer that it is the row of zeros that it has, the further up you are allowed to push, you are forced to push the ranks of the extreme rays. So if in the third row there are only zeros forever, which is what happens in the case of two regular varieties, the only extreme rays you are left with are those of rank 1, and this is why the equality holds. Okay, so this is the classification. So I think that I'm about to be done. So let me just revisit the take-home message of this talk, and maybe we'll see it with new eyes, as if it was for the first time. So what we have discussed is that there is a class of projective varieties which are, objectively speaking, the simplest that are not linear subspaces. They are called two regular varieties, and were completely classified by Eisenbot, Green, Hewlett, and Popescu in 2004. Perhaps because of their simplicity, they appear in many parts of mathematics, in combinatorics as chordal graphs, in classical algebraic geometry as varieties of minimal degree, in convex algebraic geometry as ideal worlds, where Px is sigma x, and hopefully they will appear in many other places in your research. So thanks very much. I think this is what I wanted to say. Maybe one last comment. So I put this slide to remember out of all the many things that I could not say during this talk. So if you like this subject of convex algebraic geometry, please do take a look. There is many more things. What I gave in the talk is like 1/3 of this paper. There are many other things. It's an exciting and very nice thing. And I should have a picture of my co-authors, but I did not have the time to put one. But the advantage is that they are here in 3 dimensions. So please, yeah, they are Greg Bleckerman, Rainer Sinn, and Greg Smith, with whom all this work was done. Okay, thank you.
All right, we'll go. Thank you, Mauricio. Are there any questions? Who should I like to throw the... Oh, yes. We will try.
Pretty good.
Okay, so could you please elaborate on the last statement you had about relating Betti numbers and the rank of those matrices? Like, what is the main idea?
Yes. So the key point is that if you have an extreme ray which is not of rank 1, then this extreme ray has a kernel, and one can show that this kernel has no solutions. Okay, that it's a base point free linear series. And the point is that such a base point free linear series will generate lots of quadrics in the ideal, and it will end up killing the space for the extreme ray when the resolution is sufficiently large. So it's really about a question about what's the smallest number of quadrics that a base point free linear series can generate on a variety. And this is thanks to results of yeah, Eisenbot, Green, Popescu, people like this, they understand these problems very well, and this is what we were able to use in order to prove our results.
Thanks.
Do you have an intuition how you can constructively compute these extreme rays?
I was talking to Joao on Monday, and he mentioned that the way you do it is you just sample directions and solve optimization problems, which you can do because sigma x2 is a spectrohedron. So if you just want to produce extreme rays, this is something that you can do very, very explicitly. The question is, how do you actually prove that these are all? Of course, that needs some ideas. But the methods to at least obtain a list, and probably a list that will give you a sense of what are the possibilities. Of course, they are infinite in number, no? So my procedure will only give you some examples, but it's a way of producing some, and then maybe one can develop a general theory saying that these are all. Ben.
So what is the statement of the classification theorem?
Oh, thank you, Baron. So the statement of the classification theorem is the following. So there are actually two statements, and they depend upon whether you want to think that two regular varieties are like varieties of minimal degree or like chordal graphs. So since you asked the question, I am going to do the like chordal graphs thing. Let's see where it is. Here it is. So I need a definition first. A sequence of varieties, x1 up to xn, is linearly joined if for every j between 2 and n, the following equality holds. So you take your jth variety and you intersect it with the union of all the previous ones, and that has to be the same as intersecting the linear span of your variety with the linear span of the previous ones. Okay, this looks a little weird. It's a definition one has to get used to. And the theorem is precisely that a variety is too regular if and only if its irreducible components are varieties of minimal degree, and they are put together in a way which is a linear join. So it's an ordering of the components. It's really analogous to, you remember the slide where we had all the cliques? Yeah, and we listed the cliques according to the perfect elimination ordering. That listing of the cliques has this property. And it turns out that you can always order the components in this manner, but it's very cool because much like chordality, it's a property that in principle does not depend on ordering. But if you take your variety and you choose a different ordering, it might fail. So that's one definition. And the other one is, when you think of them that they are like varieties of minimal degree, is this concept of smallness. A variety is small if for every linear space which intersects it at finitely many points, the intersection is a linearly independent set. And it turns out that two regular varieties are precisely the small varieties. So like of minimal degree, but being reducible is something that you can fix with this concept of smallness. All right.
So yeah, so on the question of sampling, I think sometimes it is actually not so easy to sample. So if you have, this is something that we don't understand, if you have a variety that, let's say, where the dual cone doesn't have so many extreme rays of rank not equal to 1, then sometimes in practice it's actually quite hard to sample an extreme ray of rank not equal to 1, and that is something that we don't really understand as to why. You know, can you put some sort of a quantitative measure on why does this happen, that you often end up at the rank 1 extreme ray? That would be something that is an extremely interesting question, but we don't really know how to address. Anybody else?
Bernard.
Yes, Bernard.
So does this property of extreme rays translate well with Veronese map?
So what the Veronese map does is that it will make you work in forms of much higher degree. So one should expect that the extreme rays of forms of degree 2D and the extreme rays of forms of degree 2 don't really have too many relations between them. So I would say no is the answer, yeah. Mike.
So what about 3 regular, 4 regular? Does it just become completely wild at that point, or is there still some sort of
we have no idea. This is a very good question. We have no idea. Which, yeah, I suppose we need good examples of 3 regular varieties that one can kind of understand. So, yeah. So, for instance, the N2P property could jump anywhere, and you still get a 3 regular variety. And in many of the examples we have seen, this bound that we have is actually sharp. So, for instance, we can prove it's sharp for graphs. So among 3 regular varieties, you will already have a huge range of possible ranks of extreme rays. And it's not clear what happens, yeah. So what I'm saying is, even if you restrict just to 3 regular varieties, it's not clear that this imposes any constraint whatsoever on the structure of the extreme rays of the dual.
More questions? Let's take Mauricio
again. There's a quick announcement by Peter Burgess. Yes, just
hello.
A second.
My name is Peter Burgess. I'd like to make a short announcement, but it would be nice to open a web page.
You can use the box.
Browser. Here's the address. Earhart. It's written here. mat.fu_Berlin.de. And I think AG plus, right, that one. That's already. Okay.
Maybe I looked at it already.
Ah, you looked at it already. Okay. Great. So there will be a special semester in Berlin. We call it Thematic Einstein semester on algebraic geometry, varieties, polyhedra, and computation. And maybe I should use that. Better? Okay. So the topic of this special semester is closely related to this conference, so algebraic geometry and its applications. So maybe you know that Berlin was successful in getting a research cluster, so we get money. Now we have this research center, MAT+, so we get money from there and also from the Einstein Foundation. We have quite a number of activities. Some of them already happened, like there was a summer school in Leipzig, which is related. In about a month from now, okay, it's the wrong one. Okay, thank you. In about a month from now, we have a conference on complexity of numerical computation. It's dedicated to Philippe Kucker, to his 60th birthday. It will be in a very nice place, in the Berlin-Brandenburg Academy of Sciences. Then we have a workshop in real algebraic geometry. Then there is a fall school. So I don't know, I should open it maybe. So there will be 4 mini courses by Greg Bleckerman, Davai Chen, George Ottaviani, and Bernd Sturmfels. Then we have a conference. I can go back here. And there will be more activities. We are still planning it. So please check out these web pages and consider attending. Thank you very much.